Over the past century, physicists have been fascinated by the concept of black holes, with the concept gaining traction around 1916. These cosmic anomalies include some of the most captivating and enigmatic phenomena we know, sitting at the convergence of enormous gravitational forces and a baffling disappearance from our comprehension. A black hole, possibly weighing between 2 and 4 million times more than our Sun's mass, continues to be an enigmatic presence in the cosmos. Despite decades of intense research, our understanding has expanded from having very little knowledge to piecing together more details, with even more new discoveries made recently. A breakthrough by Michio Kaku has revealed shocking insights into the interior of black holes that may pose a threat to long-held beliefs and provide new perspectives on the nature of these celestial bodies. This new information opens doors to deeper explorations into what might not have been considered prior. Now, come along with us as we move further into the fascinating world of black holes and uncover what's hidden within the universe's vast and inspiring expanse. But what exactly are black holes? Before we examine the most recent findings by Michio Kaku, it's essential to revisit the basic comprehension of black holes. Most of us have at least an overall understanding of what a black hole is, but there are still a few key elements that remain a mystery. Albert Einstein's groundbreaking theory of general relativity predicted the existence of black holes. At the time, the concept was only theoretical. It wasn't until roughly 50 years later that evidence was discovered confirming the existence of space-based objects known as black holes. This revelation came in the 1960s during studies of the bright star X1, a celestial body emitting X-rays. Observations showed that these X-rays were not just moving at random but were being pulled into an invisible, dense mass. This mass was later determined to be a black hole. The discovery was monumental. It changed our perception of the cosmos, proving that black holes were not figments of Einstein's imagination but tangible, elusive entities that warranted further investigation. As a result of this groundbreaking discovery, scientists worldwide began a global search to learn more about black holes. Their efforts resulted in the discovery that the Milky Way alone may host around 100 million black holes. However, due to the challenges in detecting them, black holes remain incredibly difficult to pinpoint. Scientists believe that these massive entities number in the millions and are hidden within our galaxy, making it even more important to comprehend them. Let's break down the core concept of gravity. So much force is exerted by black holes that anything entering their domain is squeezed into a singularity, a point at which the rules of physics as we know them cease to function. In simpler terms, black holes are like gigantic vacuum cleaners, pulling everything into them. One of the most terrifying aspects of studying black holes is imagining if someone were to fall into one. They would gradually be stretched out and become part of the singularity, their body torn apart by intense gravitational forces before the point of total devastation, something best avoided by not getting too close. Despite being dispersed throughout the universe, the black hole that is nearly 500 light-years away still raises legitimate concerns. In 2021, scientists achieved a historic milestone by capturing the first clear image of a black hole, the M87 black hole. This accomplishment was made possible by countless nights spent photographing and stitching images together to form a single cohesive picture. As more data was gathered, researchers were able to discern that there are 3 distinct layers to black holes, contrary to the common misconception that they are just endless voids. The first of these layers is called the event horizon, which marks the point beyond which nothing can escape. Once something crosses this boundary, it is bound to gravitate toward the black hole. The second layer, known as the photon sphere, is where light becomes trapped and unable to escape because of powerful gravitational forces at play. Finally, there is the singularity, where all matter is compressed into an infinitely small point, a place where the very fabric of reality collapses and all known laws of physics break down. What's even more intriguing is that each black hole is distinct in its own way. While they follow the general 3-layer structure, their behaviors can vary significantly. This makes them particularly challenging to study, as conventional scientific methods don't apply. Researchers are compelled to investigate these anomalies through indirect means, such as observing the radiation emitted from them or analyzing the gas and dust swirling around them. Directly inserting a probe into a black hole is an ineffective exercise. Anything that passes through the event horizon is inevitably pulled toward the singularity, where it is crushed into nothingness. Since this fate cannot be avoided, billions of dollars cannot be spent on investigations that would ultimately fail to produce valuable data. As a result, researchers are left to investigate black holes from 2 perspectives. Despite them being 3-dimensional singularities, one of the most complicated aspects of black hole research is that no 2 black holes are identical. When we study them, we must consider the breakdown of physics as we know it. Theories regarding the history of black holes suggest that they may form when massive stars collapse in on themselves. As a star exhausts its fuel, it can no longer produce enough energy to counter the inward pull of gravity, leading to its eventual collapse into a black hole, if the star is massive enough. This process continues until the matter collapses into a singularity. To gain a deeper comprehension of their nature, NASA scientists turned their attention to the center of the universe, especially the M87 galaxy. There, they observed a massive whirlpool of hydrogen gas spinning at mind-boggling speeds of 1.2 million miles per hour. The centrifugal force should have caused the gas to break apart, but it remained intact, suggesting the presence of a massive object at the center, likely a black hole. This object is believed to weigh up to 3 billion times the mass of our Sun. Another significant theory was proposed in 1963 by New Zealand mathematician Roy Kerr, who used Einstein's equations to describe the behavior of rotating black holes. He argued that black holes that rotate do not settle into a single point as previously thought. Instead, a rotating black hole forms a structure known as a thin ring called the ergosphere. This rotating disk of matter is essential to comprehending the disintegration of physical laws in the vicinity of black holes. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that may provide an escape route through spacetime, connecting distant regions of the universe or even parallel universes. To grasp the idea of a wormhole, it's important to understand the concept of spacetime. In Michio Kaku's mind-blowing explanation, spacetime, originally proposed by Einstein, is a warped, four-dimensional fabric affected by massive objects. This warping creates gravitational fields that influence the movement of other objects. Consider spacetime to be like a piece of paper. If you fold the paper, you create a shortcut between 2 points. This is the essence of a wormhole. As researchers venture deeper into these cosmic mysteries, they increasingly rely on technological advancements to gather and interpret data. Instruments like the Event Horizon Telescope, gravitational wave detectors like LIGO and Virgo, and space-based observatories such as the James Webb Space Telescope have opened unprecedented avenues for observation. Gravitational waves, ripples in spacetime caused by the violent merger of black holes, offer a unique method for studying events that were once thought to be undetectable. Since their first detection in 2015, these waves have provided invaluable insights into the mass, spin, and nature of colliding black holes, adding another layer of understanding to these celestial titans. But as each question is answered, more emerge. One of the most debated questions in modern astrophysics is whether black holes destroy information. According to classical physics, anything that crosses the event horizon is lost forever. However, quantum mechanics insists that information cannot be destroyed. This paradox, known as the black hole information paradox, has ignited fierce debates among the greatest minds in science, including Stephen Hawking, who once proposed that information may, in fact, be preserved in some subtle, encoded form within the Hawking radiation emitted by black holes. In this context, the interior of a black hole is no longer just a mystery, it's a battleground for two of the most fundamental theories in science, general relativity and quantum mechanics. Reconciling these two frameworks may ultimately lead to the long-sought theory of quantum gravity. The idea of a black hole as a gateway to another dimension or universe remains a captivating, if speculative, possibility. Theoretical frameworks such as the holographic principle propose that all the information contained within a black hole could be encoded on its surface, much like a hologram. This theory suggests that our three-dimensional universe may itself be a projection from a deeper, more fundamental two-dimensional reality, an idea that challenges the very nature of existence and perception. Meanwhile, M. Yakubu's controversial new insights challenge even more of what we assume to be true. Based on advanced mathematical modeling and simulations, Yakubu suggests that the singularity within some black holes may not be a point of infinite density after all, but rather a bridge to a different region of spacetime governed by unknown physical laws. If true, this would revolutionize the way we understand not only black holes, but the architecture of the entire universe. Could it be that black holes are not endpoints, but beginnings? Could they represent tunnels to other galaxies, or even new realms of reality beyond our comprehension? The idea that what falls into a black hole may not be lost, but rather transformed or transported, opens profound philosophical and scientific questions. It forces us to confront the limits of human knowledge and imagination. It compels us to ask, what is the true nature of the universe? What lies beyond the observable? And most importantly, are we prepared to know? As we stand on the cusp of new discoveries, one thing is certain: the study of black holes is no longer the exclusive domain of science fiction. It is a vibrant and dynamic field where each breakthrough brings us closer to understanding the most extreme and mysterious phenomena in existence. And while the path forward may be littered with paradoxes and uncertainties, it is also illuminated by the unwavering curiosity that drives humanity to explore the stars, and whatever lies beyond them. Understanding of the universe. Continuing from where we left off, the pursuit of superstring theory and other theories that aim to unify nature's forces is an ongoing challenge, but it holds the promise of gaining new understanding of the very nature of reality itself. These hypotheses propose that the universe is composed of more than just the three usual dimensions of space and one of time. In fact, they suggest that additional dimensions exist. However, they are so small and compact that we are unable to observe them directly with current technology. Their existence could provide the key to comprehending phenomena such as black holes, the deepest mysteries of wormholes, and more. The superstring theory of the universe provides an amazing depiction of reality, claiming that all forces and matter are manifestations of tiny vibrating strings. These strings are capable of vibrating at various amplitudes, with every vibration corresponding to a different particle, just as a guitar string can produce different musical notes based on how it vibrates. The fundamental particles of nature might correspond to different vibrational patterns of superstrings. If proven, this theory would not only provide a unified explanation for the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new ways of understanding the universe's structure. This could possibly provide solutions to some of the biggest questions in physics, including the nature of dark matter and dark energy, which together represent the vast majority of the energy and mass of the universe, yet remain largely mysterious. Despite its elegance and promise, superstring theory remains unproven. One of the major hurdles in testing the theory is that the more dimensions it has, the more its predictions are so minuscule that they are beyond our current observational capabilities. Detecting these dimensions would require instruments of unprecedented sensitivity and precision. Even then, the evidence may be so indirect that it makes string theory a difficult subject to test using traditional scientific methods. Yet its mathematical beauty and coherence make it one of the most compelling ideas in theoretical physics. Simultaneously, scientists are working on other approaches that might lead to breakthroughs in our understanding of black holes. For example, quantum gravity is another field of research that seeks to combine the principles of quantum mechanics, which govern the behavior of subatomic particles, with the theory of general relativity, which explains the behavior of massive objects such as planets and stars. The hope is that by merging these two theories, scientists can acquire a more precise understanding of how gravity works on the quantum level, and in turn gain deeper insights into the nature of black holes and other cosmic phenomena. The intersection of quantum mechanics and general relativity is especially crucial when studying black holes, because the extreme conditions near the event horizon, where gravity is extraordinarily intense, demand a theory that can account for both quantum and relativistic effects. The interior of a black hole, where the singularity lies, is one of the most perplexing and bizarre environments in the universe. The singularity is the point at which space and time become so warped that the usual laws of physics break down. Understanding what happens in such a place necessitates a theory that reconciles quantum mechanics and general relativity. This has led to the development of ideas like loop quantum gravity and other quantum gravity models, which aim to resolve these contradictions and supply a deeper, more complete picture of black holes. As we keep looking into the mysteries of black holes, one thing is for sure: the more we learn, the more we realize how much there is still to discover. Black holes are not just points of destruction, but are also places of incredible complexity and potential. Whether they serve as entry points to other dimensions, as some theorists believe, or whether they hold the key to comprehending the most important aspects of space and time, black holes remain a crucial area of study. As our tools and theories evolve, so too will our understanding of these enigmatic objects. Looking ahead, the next major challenge will be to improve our approaches to observing and studying black holes. One of the most exciting innovations in recent years has been the development of gravitational wave astronomy. Gravitational waves are fluctuations in spacetime caused by the movement of massive objects, like the merging of black holes. By detecting and analyzing these waves, scientists can learn about the behavior of black holes and other celestial objects in ways that were previously unattainable. The identification of gravitational waves has already provided revolutionary insights into the dynamics of black hole mergers, and future experiments are likely to yield even more revelations. In addition to gravitational waves, another promising area of research involves the use of advanced telescopes and imaging techniques. The Event Horizon Telescope, EHT, which produced the first image of a black hole in the M87 galaxy, is an example of how innovative technology can shed new light on black holes. By combining data from multiple radio telescopes around the world, the EHT was able to capture an image of the black hole's shadow, offering a glimpse into one of the universe's great mysteries. As technology continues to improve, it's likely that we will be able to observe black holes in even greater detail, revealing more about their role and behavior in the cosmos. Black hole research is not just about understanding these strange objects on their own, it's also about understanding the fundamental workings of the universe. Black holes are essential to our knowledge of space-time, gravity, and the very nature of reality. By studying them, we are not only learning more about these objects themselves, but also about the laws that govern the universe at its most extreme scales. In conclusion, the study of black holes is one of the most exciting and challenging fields in modern physics. With each new discovery, we inch closer to unraveling the mysteries of these cosmic giants. Whether through the study of gravitational waves, advancements in imaging technology, or the emergence of brand-new hypotheses, black holes continue to captivate the imagination of laypeople and scientists alike. As we explore the universe's most extreme and enigmatic objects, we are forced to confront fundamental questions about the nature of space, time, and existence itself. In doing so, we may be on the brink of unlocking some of the greatest secrets of the universe, perhaps even obtaining answers to questions that have eluded humanity for millennia. As the scientific community pushes forward, interdisciplinary collaboration is becoming increasingly vital. Physicists, mathematicians, astronomers, and engineers are joining forces to develop new instruments, models, and computational methods capable of probing the frontiers of knowledge. Supercomputers now simulate cosmic phenomena with astonishing accuracy, enabling us to test theories that were once purely speculative. These virtual laboratories allow researchers to explore how black holes evolve, interact, and influence the structure of the universe on both small and vast scales. At the same time, philosophy and cosmology intersect in compelling ways. The deeper we delve into the nature of black holes, the more we confront questions that challenge not only our understanding of physics but also our perception of reality itself. What does it mean for information to be lost in a black hole? Can it be retrieved, or is it transformed in ways we can't yet grasp? The information paradox, famously highlighted by Stephen Hawking, continues to spark debates and theoretical developments. Some hypotheses suggest that information may be encoded on the event horizon, a concept related to the holographic principle, which proposes that our three-dimensional universe might itself be a projection of data stored on a distant boundary. This radical idea, though still unproven, hints at the possibility that space and time are not fundamental, but emergent phenomena, arising from deeper, underlying principles not yet fully understood. If such theories are validated, they could revolutionize not only our comprehension of the universe but also the very framework through which we interpret existence. Meanwhile, advances in observational technology, such as next-generation space telescopes, hold the promise of expanding our vision even further. Instruments like the James Webb Space Telescope and future missions like the Laser Interferometer Space Antenna, LISA, will offer unprecedented resolution and sensitivity, potentially unveiling phenomena that have eluded detection until now. These tools will allow us to peer deeper into the cosmos, perhaps even witnessing the birth of black holes or capturing gravitational echoes from the early universe. Each step forward brings with it a profound sense of wonder. The study of black holes reminds us that, despite all our progress, we are still at the beginning of a vast journey. The universe is not a finished puzzle but a living, breathing enigma that invites curiosity, creativity, and courage. It demands that we ask bold questions, confront paradoxes, and remain open to the possibility that reality may be far stranger, and more beautiful, than we ever imagined.